Welcome. Today I'm going to be talking about recurrence relations and how to solve them. So first we're going to start with what is a recurrence relation and what does it mean actually to solve a recurrence relation. So the setting here is they come up in sequences, and sequences especially you can see them in discrete math, combinatorics, computer sciences. But in any area of mathematics, actually, you can encounter sequences, and inductive definition of sequences or the recursive definition, they are interchangeable terms, versus the closed formula. So what is a recurrence relation? It's a formula relating a term of a sequence to previous terms along with the values of initial terms. So for example, a of n equals 5 times a of n minus 1, and where a of 0 is equals 1. So this is the simple case of it's probably you can recognize it right away, is a geometric sequence. The way we define geometric sequence is you go from one term of the sequence to the next, multiplying by the same number, the same constant. Whereas for arithmetic sequences, you go from one term to the next, adding the same number or constant, or same fixed number. Now, most of the other sequences are neither arithmetic nor geometric. Another example can be, for example, b of n equals 4 times b of n minus 1 plus 1, where b of 0 is equal to 2 raised to the power of negative 1. Or 1/2. Also, one thing that I wanted to note here, because it's not just the definition of n plus first or nth term in terms of the immediate previous term, but it can be the n plus first term in terms of two immediate or two previous terms, or more than two. There is no limitation on that. So, for a very famous sequence called Fibonacci sequence is defined as following. F of n plus 1 equals f of n minus 1 plus f of n, where f of 0 equals 0 and f of 1 equals 1. Okay? Now, one word about the values of initial terms. You cannot change those values and get the same sequence. The structure may be the same, but the sequences can be very different. They might look very different from each other. And you can try that by switching or changing or making the initial values different from what you see here, even starting with negative or starting with f0 being greater than f1, and you are going to end up with a sequence that is going to be very different from what is known as typical Fibonacci sequence. Alright, what is a closed formula now? Closed formula is when the nth term of a sequence is given in terms of n. So, in order to find what is the value of the term in a certain position, all you need to know what the position is, and using this formula you can find the value of the term. So, a of n, for example, equals n times n plus 1 over 2. So this is a formula that gives you the nth term only in terms of n, not in terms of previous terms, like it was the case of recurrent relations. And by the way, this is the sequence of triangular numbers that is known. For the Fibonacci sequence, the closed formula is this one. It's more complex. It's f of n equals 1 plus square root of 5 raised to the power of n minus 1 plus square root of 5 raised to the power of negative n over 5 times 2 to the power of n. As you can see, you can imagine it's not as easy to go from this definition of Fibonacci to go to the closed formula. But that's what exactly means to solve a recurrence relation. So when you are able to convert or to start with a recurrence relation and to find from there the closed formula of that sequence, that means that you have solved the recurrence relation. So without any further ado, let's look at one example, but different methods. Here is the recurrence relation. A of n plus 1 equals 3 times a of n plus 2, and a of 0 equals 1. So this is a simple, relatively simple recurrence relation. And the first method to solve this would be iteration. So what's iteration? You simply start with the inductive step, start with a of n plus 1, and go to find the pattern that is going to be created when you go from n plus first to the nth term, from nth term to the n minus first, from n minus first to n minus second, and so forth. So let's take a look at that. So a of n, based on this formula, on that recurrence, is going to be equal to 3 times a of n minus 1 plus 2. So if you substitute that to the definition of recurrence, a of n plus 1 is going to be 3 times that expression plus 2. Multiplying is going to be 3 squared times a of n minus 1 plus 3 times 2 plus 2. Don't add up these terms because they are going to help us to see the pattern that is going to be formed. Okay, now we went down to a of n minus first. Let's go from there to a of n minus second, or a of n minus 2. So substituting is going to be 3 times a of n minus 2 plus 2. That's what a of n minus first equals to. So 3 squared times that a of n minus 1 in terms of a of n minus 2, right? Plus 3 times 2 plus 2. Doing the multiplication, you get 3 cubed a of n minus 2 plus 3 squared times 2 plus 3 times 2. And in order to fit into the pattern, we can write 1, you can see it's not visible, 1 times 2, but you can write 1 as 3 to the 0. So multiplying by 1 does nothing to the number. So, but it helps us to see the pattern. So you go 3 to the raised to the power of 0, 3 to 1, 3 squared, and each of these terms is multiplied by 2. Let's do one more and see, is that trend going to continue? So if you substitute now a of n minus 2 in terms of a of n minus 3, you are going to get 3 cubed times 3 times a of n minus 3 plus 2 in parentheses, and then the tail, the same as above. Doing multiplications here, 3 to the 4th, a of n minus 3 plus 3 cubed times 2, 3 cubed times 2, 3 squared times 2 plus 3 times 2 plus 3 raised to the power of 0 times 2. Now the pattern starts to become clear. What is the pattern? So the tail here is clear, is going to be 2 times a power of 3, and starts 3 raised to the power of 0, 3, 1, 3 squared, 3 cubed, and so forth. Now, we are going to go down up to a of 0, right? One thing that you can notice here, the sum of the power here of 3 and the index of a is always n plus 1. So n minus 3 plus 4, n plus 1. Or n minus 2 plus 3, it's n plus 1. n minus 1 plus 2 is n plus 1. So when you want to go, you don't have to do every single step because you don't know for real what the value of n is, but just so that you see the pattern, you are going to arrive to the point where you are going to get 3 raised to the power of n plus 1 times a of 0 plus 3 to the n times 2, 3 to the n minus 1 times 2, and so forth. The last one, 3 to the 0 times 2. Now it's clear the tail here is going to be easy calculation. It's a geometric sequence, and you know how to find the sum of the geometric sequence, finite sum. So in that case, if you want, you can figure out 2, and the formula for the sum of finite geometric sequence is going to give you 3 to the n plus 1 minus 1 over 2. 3 minus 1 is 2. 2 and 2 cancels out, so the closed formula is going to be a of n plus 1 equals 2 times 3 to the power of n plus 1 minus 1. You see, this is a nice formula, and you have the n plus first term in terms of n only. And it's not a problem, you can go to the nth term in terms of n. So it's going to be a of n equals 2 times 3 raised to the power of n minus 1. Right? Let's see another method. The second method that we're going to see that is going to help us to solve the same recurrence relation is the matrix method. Matrix method probably is not as efficient as the other methods, but what's interesting here is that it seems like matrices and recurrence relations seemingly have no connections between them, but this method somehow connect those two areas to different concepts in mathematics in a nice way. Although it's a bit long, I mean, I like this for that reason, for making those connections between different areas of mathematics. Now let's, without any further ado, let's look at this method. So we had our recurrence relation that is here, a of n plus 1 in terms of a of n. From there you can define what is going to be a of n in terms of a of n minus 1. Subtracting these two equations, you are going to get a of n plus 1 minus a of n equals 3 times a of n minus a of n minus 1. If you solve this for a of n plus 1, you are going to arrive to the conclusion that a of n plus 1 equals 4 times a of n minus 3 a of n minus 1. So you are gonna, I mean, you can express actually this equation in matrix form, in a very nice way in matrix form, using the vector now a of n plus 1 a of n, and the matrix that is going to be multiplying the other vector a of n minus 1 is 4, negative 3, 1, 0. And you can check. If you do the multiplication 4 minus 3 by this column, it's going to give you a of n plus 1. It's this formula. A of n plus 1 is equal to 4a of n minus 3 of a of n minus 1. And of course, then a of n is equal to a of n. So that's given, and that's what the other multiplication, the row times this column, is going to give you. Now, what's the point of this? The point is that this is similar to the progression, the geometric progression thing or geometric sequence thing, but in the matrix form. So you go from n plus 1 here to n multiplying by a matrix. And you understand the pattern. You can go from a of n minus 1 to a 1 degree lower, 1 index lower, multiplying by the same matrix, right? So it's going to come down to calculating the powers of the matrix M, 4, negative 3, 1, 0. And the question is there any easy way how to calculate the nth power of this matrix? Yes, if it's diagonalizable. If they have entries that are non-zero, and everywhere else you have only zeros. Well, what is good about these diagonal matrices? Good about them is that when you raise them in the nth power, the result is going to be you simply raise every entry in the main diagonal to the nth power. So it's an easy calculation. You don't have to do multiplication of matrices that are complex. But what is how you can know beforehand whether or not a matrix is diagonalizable? So diagonalizable when you can write M in the form P d times P of raised to the power of negative 1. P must be invertible, clearly. And D is a diagonal matrix. So if you can write M in this form, then M is going to be diagonalizable. Okay? So one criteria, a nice one, is using eigenvalues. And in this case, in our case, we are dealing with a 2 by 2 matrix. So all it's required, if you have two different eigenvalues for this matrix, then this matrix is going to be diagonalizable. And we can check right away that there are two different eigenvalues. So for this, you can solve this polynomial equation. It's the characteristic polynomial of that matrix. Solving that, you arrive to a second degree equation which has solutions. It's lambda squared minus 4 lambda plus 3 equals 0. And the solutions for this are going to be 1 and 3. It's very easily checked. You can see that. So from here, we can make the conclusion that our matrix M is diagonalizable. Now, can we find P? What is P? This actually, the eigenvalues help you identify what P must be, but I'm not going to focus on that. It's simply a process. Everyone can look at how you can how you can do this process, follow this process. I'm going to provide what P is, and we can continue with the idea. As I said before, the proof of this, or using this, is a bit long, so we are going to skip some of those procedural steps to give you the essence of this method. Okay, let's continue with the matrix method, the second method that we are looking at solving this recurrence relation. So the idea was, can we rewrite that matrix in this form, P times D times P to the -1, so the inverse of that matrix, where D is a diagonal matrix. And we settled the issue that this matrix M is diagonalizable, and P turns out to be 1, 3, 1, 1. So, substituting that, you can calculate what M to the power of N is. Of course, there are not many calculations for the inverse of this matrix, so it turns out to be -1/2 times the matrix is going to be 1, -3, -1, 1. Okay, so if you remember, we had the vector A of n plus 1, A of n, equals M to the power of n times, it's going to be A1, A0 at the end. So substituting what is n to the n, this thing, and what is A1 and A0, in case when A0 is 1, you can calculate what is A1 right away. It's going to be 3 plus 2, it's 5, so you have to multiply by the vector 5, 1. And at the end, if you do the calculations correctly, so it's a procedural thing, so the main idea is to get the concept of this method. So at the end, you're going to get the same result that we had with the iteration method. A of n plus 1, A of n plus 1 is going to be 2 times 3 raised to the power of n plus 1 minus 1. Okay? Now let's look at another method. The last one, it's much shorter than this one, and it's my favorite method. Okay, it's using some dynamical systems kind of idea, and it's really quick. Okay, so let's go to the method number 3. The third method, how to solve this recurrence relation, is the fixed point method. Okay, let me change the number here. It is the third. All right, and the idea is simple. You can look at this recurrence relation as an inductive defined function. So f of x equals 3x plus 2, and you can find the fixed point for this function, which is the point at which f of x equals x. Solving that equation, it's a simple linear equation, you get x equals -1. So you're gonna make a shift, a translation to the original sequence minus the fixed point. So since the fixed point is -1, then the translation is going to be u of n plus 1. So we define a new sequence in terms of the old one. It's going to be a of n plus 1 plus 1. So whatever the nth term of this sequence is going to be the nth term of the original sequence plus 1. So that's where the shift is. Okay? And so you can go u of n equals a of n plus 1. And so fourth u of 0 is going to be a of 0 plus 1. Now, substituting, since we know the recurrence, substituting a of n plus 1 in terms of a of n, we are going to get 3n plus 3, which can be rewritten as 3 times a of n plus 1. And substituting back, a of n plus 1 is u of n, so you get u of n plus 1 is 3 times u of n. So u of n on its own is a geometric sequence. So you can find the formula rather easy, the general term of the sequence. So u of n plus 1 is going to be 3 raised to the power of n plus 1 times u 0. Substituting back to the original sequence, the term of the original sequence, we get a of n plus 1 equals 3 raised to the power of n plus 1, a of 0 plus 1. Since a of 0 was 1, a of 0 plus 1 is 2, which gives you a of n plus 1, 2 times 3 raised to the power of n plus 1 minus 1. So it's the same result, but it's much quicker than the other two methods. So these were like 3 methods you can use to solve a recurrence relation. I mean, as I mentioned before, this is my favorite. Downside for this method is that not always can be applicable. There are cases of recurrence relations where you cannot use this method. So iteration, usually it's better off in terms of how general that method can be. So iteration works most of the time, but there are always, sometimes you have to be creative with methods that you use to solve a recurrence relation. But if you keep in mind these 3 methods, if you are working with not very complicated recurrence relations, those are going to be working in general. Okay? So next time I'm going to focus on a specific recurrence relation. It's an interesting one. So it's one of those cases when sometimes it's challenging to have an application and come up with a recurrence relation. So compared to here, I mean, here the recurrence relation is given, but in that situation you have to find out what is the recurrence relation and then solve that recurrence relation. Okay, so until next time, have a good one.